Okay, hi class. So we're doing 4.4 now. We're talking about graphing log functions, and I just want to explore the general shape of what they look like, and also talk about their domain. And once we know that, then we'll just explore how to graph them and how to use them to deal with things. And of course, I'm going to be graphing a little bit by hand a little bit, but also a little bit with the calculator. And you're completely fine using a graphing calculator as well to graph your logs. It's completely fine with me. So first, let's just kind of recap what we talked about last time. Domains of logs are important because the domain is not going to be all real numbers. In general, for a log function, I'll call it log base b of x. Okay, in general, it has a domain of this 0 to infinity, so it can only be positive numbers. Those are the only numbers that are allowed to go inside the log. Inside here, fancy word for that is called the argument. So the argument of logs can only be positive numbers. It just means that when you put a number into a log, the only numbers that are allowed to be put into a log are positive numbers. So this is the same for this log base 2. This is on this problem, it's specifically log base 2. Well, it's going to have, again, the same domain. It's going to have 0 to infinity as its domain. And you can tell from the graph too, because here it's in blue, log base 2, okay, it has this vertical asymptote right here, like that, and that's the x equals 0 asymptote. And so we see that it can't go to the left of 0, it can't equal 0, but it comes up after that, and it goes on forever. And there's no problem going to the right. So really the only problem is that we can't have 0 or negative numbers. Okay, so in general there always will be a vertical asymptote when we get close to the restriction. On the domain. In this case, for a log that's not shifted, the restriction is 0. And so x equals 0 is my vertical asymptote. So this happens whenever the inside of the log, I shouldn't say is, but I should say approaches 0. And the fancy word for the inside, again, is the the argument. It's just what's inside. So let's take a look at an example here. It'll make it really clear. Change my pen here. So what's the domain of this log? Well, all that we do is, again, we just care about, okay, we simply set x plus 3. Okay, the inside of a log always has to be positive. So the way we write it as has to be positive is that it has to be greater than or equal to 0. So if x plus 3 is greater than 0, then we just subtract 3 and we get our domain. And so we get x is greater than 3. That's my domain, but of course we want to write it in interval notation, and so we write it as 3 to infinity. Okay. So go ahead and you try. Can you try to find the domain of this log function? Go ahead and work on it, pause the video, and then come back and we'll take a look at the answer. Okay, and we're back. So this is what I got for the domain. The domain has to be, x has to be bigger than 2, and so the domain is going to be 2 to infinity. And hopefully you got the same answer. Some of you might have worried about what about this plus 1? Does that affect it at all? That has no effect. The only thing that matters about a log, about its domain, is the argument, is the thing inside the log. Anything on the outside, multiplying or adding or subtracting on the outside, doesn't matter. All that matters is what's on the inside. Just like your parents told you, it's not on the outside that counts, it's what's on the inside. Same thing with the log. Okay, so again, let's do it over here. Let's find the domain of this one. So again, just like before, all we do is we set the inside greater than 0. Alright, and then we just try to solve. So I'll add 2x. Those cancel, and we're left with 5 is greater than 2x. And last step, divide by 2. And you get 5 over 2 is greater than x. So this means x has to be less than 5 over 2, and so the domain is going to be negative infinity to 5 halves. Okay, so that's that one. Again, all that we do is we just set the inside greater than 0. That's how we find the domain. So go ahead and take a look at this one. Try quick check number 2, and I'll pause the video. You pause the video, you try it, and we'll come back and see what we get. Okay, so this is what I got for the domain. X is bigger than 3/4. Right there. Okay, and again, I'm trying to throw a curveball here. I have this -5 here. That does not matter. All that matters is you just set the inside greater than 0 and you solve. Okay, hopefully everyone's getting that. So what we're going to move on now is to move on to graphs of logs and to about what in general what they look like. And so I included a picture here for you. I'll do it in maybe blue here. Okay. In general, just a log function, log base b, and so the way it works is that and we just care about b has to be bigger than 1, just to make sure it's a log, not a flip log. So anyways, we're always going to make it be greater than 1. So again, they always have a vertical asymptote. So for any log that looks like this, we call this an unshifted log. It's not shifted because I'm not adding anything, I'm not subtracting, I'm not scaling, not doing anything that we learned back in chapter 1. So it's just I'll call this the general, it's called the parent function. So they always have a vertical asymptote at x equals 0, as you can see right here. Are they one-to-one? Yes. You can see from the graph, it passes the horizontal line test. It's all good. And it has to be one-to-one because it's an inverse of an exponential. Remember, inverse functions have to be one-to-one, and one-to-one functions have to be invertible. And the domain, again, for all logs, as long as they're not shifted, is the inside has to be bigger than 0. So in this case, it would just be 0 to infinity. Okay. The range is always going to be negative infinity to infinity. As you can see from the graph, it goes down to negative infinity, and it also goes up. This is increasing forever and ever. It does go up, up, and up, and up, up. Okay. The x-intercept is always going to be at this point. It's going to be at 1, 0. And again, that's because it's a inverse of the exponential functions. Remember, exponential functions always went like this. So call that b to the x. And it's a reflection across the y equals x line. Okay, the first key point is b comma 1. It's right here. And the y-intercept, is none. If you look at the graph, there's definitely no y-intercept, so no y-int. Okay, and again, because it has x equals 0 as the asymptote, it can never cross there. And we're talking again about the log function, not about the exponential function. And it's always increasing, so it's increasing on all real numbers. Okay, so keep that handy when you're talking about log graphs and stuff like that, because that helps us just identify the key parts. So for instance, this is log base 5. So if I graph log base 5, I know it's going to go through 1, 0, so that's your starting point. I also know it's going to go through 5, 1. Here, again, b is equal to 5. So my key point is going to be 5, 1. So this will be 1, 2, 3, 4, 5, 1, like that. And I know it has a vertical asymptote right here at x equals 0. And so that's really all I need to be able to graph this log function. It'll look something like this. And I can label the points here to help you. 1, 0, and 5, 1. Like that. And there you go. Of course, we could also use a graphing calculator, but I want us just to get a general idea of what they look like first before we move to the calculator. Because I also want, the calculator can't really help us with this part. And this we just have to know what these guys do. So a domain for this one, again, this is an unshifted log, so it's just like the parent function. So the domain is going to be 0 to infinity. The range, and I hope it's clear why the domain is 0 to infinity, again, okay, because it has this vertical asymptote right here. And it doesn't go past it. So it starts at 0, open though, it's an open parentheses, and goes to infinity. The range for all logs is negative infinity to infinity. And the asymptote, I already labeled it on the graph, but you can see here, this is the asymptote, x equals 0. Remember, it's a vertical asymptote, so we write it as a vertical line, x equals. And the x-intercept is right here at 1, 0. Alright? So hopefully, walking through that relatively simple example helps you see what a log looks like. It just is turned on its side like this, like we have right here. Okay. So let's move on. So let's move on to talk about using the sketching, using transformation rules. So our graph here is of log base 5, and we want to do a transformation graph, so log base 5 with all these rules. So let me I'll draw the log base 5 graph again, right here, and 2, 3, 4, 5, looks something like that. So that's the parent graph, that's just log base 5 with no shifts or anything. Okay, x equals 0, and so let's talk about what the shift graph will do. I'll draw this in blue. Okay, so what does the x plus 2 do to it? Well, remember, plus 2, when it's next to the x, your x lies about you. So this means it moves left 2. And the negative 3 on the outside means it moves down 3. Okay. And so that means I'm going to take my graph and move down 3, left 2. So I'll take this point and I'll go left 2, so 1, 2, and I'll move down 3, 1, 2, 3. So right here. And then I'll take this point, which was 5, 1, right here. I'll move left 2, sorry, 1, 2, and I'll move down 3. 1, 2, 3. And my asymptote also changes. My asymptote moves 2. So rather than being 0, it's going to be moved to the left. So I have this new vertical asymptote right here. And so the actual graph looks like this. Try to connect the dots here. Like that. Didn't really leave myself enough room. Okay, so anyways, everything got moved to the left 2, down 3, and that's the graph there. Okay, let's do another example. So here, again, I have log base 5 of x. So that's my parent graph, and I want to graph the vertical reflection and the horizontal reflection. So, good, I have more room here. So we'll take the parent graph again, which is log base 5. It has starts here at 1, 0. The key point is 2, 3, 4, 5, like that. It has x equals 0 as this asymptote, and so again, this is the same graph we've been talking about. So this is the parent graph. So let's graph the vertical reflection, do a different color. So the vertical reflection, we'll do it in red. So all that does is it just moves, it changes all the y values. So here it's still going to be here because the y value is 0. Okay, and here rather than be 5 comma 1, so this is 5 comma 1, rather than that it's going to be now be moved down to 5 comma negative 1. So it's going to be right here, like that. And then all of these negative values on the original graph, they're going to have to be shifted up to here. And so now this is what the graph looks like of negative log base 5 of x. So that's the vertical reflection. Vertical reflection. And let me do it in blue of the horizontal reflection, log 5 base of negative x. So again, in this case, you're going to take each value and swap out the x to be a negative. So here the value was 1 comma 0. Now it's going to be at negative 1 comma 0. This point here was 5 comma 1, so now it's going to be at 1, 2, 3, 4, 5. And the y is going to be the same. It's going to be over here. So now this is going to be negative 5 comma 1. And all these guys, which were positive x values, are now going to be swapped over here to be negative x values. And so this is my graph. And so that's the log of negative x. Okay, so we have in black the original graph. We have the vertical reflection here. It went, basically just up and down. It switched spots up to down. And the blue one is the horizontal reflection, which just means it moved left to right. So it's just a mirror image across the y-axis. Okay, and that's pretty much all I wanted to do for this section. So just talk about just kind of the general features of these graphs, and that's it. So we'll move on to the next section, and I'll post these notes on Canvas and you can start the homework. Thanks.